This is now part B1 of the June 2018 Physics Regents, where we go over questions 36 to 50. These are a different set of questions than the first 35 in part A. And so we start with number 36, which is always a metric estimation type question. And typically they ask you about estimating mass, they ask about estimating height or distance or length of something. And they usually put these answer choices lately in the past couple of years in scientific notation to the base SI unit. And so when we're estimating the height of an individual step, all of our answer choices are in meters, and we need to be able to sort of convert it back to standard notation and also know in our heads what this sort of size looks like. And so an individual step on a staircase, let's first convert each of these to meters. So choice 1, 2 times 10 to the negative 2. If you don't know, on your reference table on the first page, they have the SI unit prefix conversions. And so this 10 to the negative 2 is the same as 2 centimeters. Choice 2 is 0.2 meters or 20 centimeters. Choice 3 is 2 meters, because anything to the 0 power is 1. And then choice 4 is 20 meters. So maybe in your classroom experience, you definitely have seen a meter stick or a yardstick or 3 12-inch rulers stacked together approximately. And so if we look at our choices, we could easily eliminate choice 3 and 4 because a staircase step should not be 2 meters or longer. And so we're looking at 2 centimeters or 20 centimeters. 2 centimeters, I would like to sort of equate that almost to an inch. Is an individual step an inch long, an inch high? No, it's actually too small. 20 centimeters is about 10 of 10 inches about. That's about less than a ruler height. And so I'm going to go with choice 2 as our answer. 20 centimeters seems the most appropriate. Okay. Number 37. What is the magnitude of the electrostatic force exerted on an electron by another electron when they are 0.1 meters apart? So let's first identify things. So we are looking for magnitude of the electrostatic force, that is Fe. We have 2 electrons, so their charges, both of them are going to be identical. 1.6 times 10 to the negative 19 coulombs, that's elementary charge on the front of your reference table. That's for an electron or proton. And their separation distance is 0.1 meters. Now pause for a moment so you can figure out which equation you're going to need. There's only one equation that fits all of these things together, and I'm going to pause it here. Okay, so I gave you the equation, I gave you the substitutions. K is a constant that you could also find on the front of the reference table, right here with this value. Q1 and Q2 are multiplied together, and since they're the same value, I just squared it, and then R is 0.1 meters on the bottom. Don't forget it's squared. That's a common mistake for people to leave out, is that it's squared. And so you're left with this answer of 2.3 times 10 to the negative 26 Newton, and that's choice 3. If you get choice 2, that means you forgot to square R on the bottom. Okay. Number 38. After a 65 Newton weight has fallen freely from rest, a vertical distance of 5.3 meters, the kinetic energy of the weight is blank. Okay, so here we have a weight that starts about 5.3 meters high. So this is its starting point, and this is its end point. And this is a difference of 5.3 meters high. At your starting position where it's dropped, it has max potential energy that's equal to mgh, where down here it has max kinetic energy equal to 1/2 mv squared. We need the kinetic energy, but we don't have any speeds here. We have a weight which we can convert to mass, but we don't have any indication of a speed. There are a number of ways you could calculate this. Actually, it'll be hard to calculate through kinematics, but you have to do it through the conservation of energy method. And so we have to know that the relationship between our start at the top and our ending point at the bottom is that they're equivalent to each other. You start with all this energy at the top, it converts to kinetic energy. And so we can easily find our potential energy at the top and know that it's equal to the kinetic energy at the bottom. So mgh, 65 newtons, that's already mg, that's the weight. So 65 newtons is mg times the height of 5.3 meters, and that'll get us our answer of about 340 joules. I just did the math in my head. Choice 2. Number 39, a 0.5 kilogram car traveling to the right on a horizontal frictionless surface at 2.2 meters per second collides head-on with a 0.8 kilogram cart moving to the left at 1.1 meters per second. What is the magnitude of the total momentum of the system after the collision? So let me pause to draw this out for you. Okay, so here we have our two objects colliding. They're coming in opposite directions. They collide head-on. And we need our total momentum after. But its relationship to its momentum before the system is that they're equal. These two things, total momentum before equals total momentum after, because of conservation of momentum law. So we only have information before the collision, and so we could use all of that, get the total before to equate it to after, and that's it. Now, the thing to keep in mind is that both of these cars are coming in at opposite directions. And because of that, because these are vectors, we have to take the difference of their magnitudes. Okay, so momentum is simply mass times velocity. I hate when this happens. Okay, I'm ready. So 0.5 kilograms times 2.2 meters per second minus 0.8 kilograms times 1.1 meters per second. That's our total. And you get 0.22 kilograms meters per second. And the reason we have to subtract them is because they're coming in opposite directions. If they followed the same direction, then we would add them. And we get choice 1, because momentum is a vector. All right, number 40, an object weighing 2 newtons is pushed across a horizontal frictionless surface by a horizontal force of 4 newtons. The magnitude of the net force acting on the object is... Alright, so let's first draw an image here. 2 newtons is the weight of the box, as well as the force pointing downwards, and the force pushing back up, called the normal force. So this is Fg, and then normal force is equal to the weight. And it's being pulled across with 4 newtons. It's frictionless, so there's nothing on the opposite side here. There's no friction. Now, top and bottom are canceling out, and left and right are unbalanced, so there is a net force here, because there's no friction. And so our net force is just 4 newtons. That's it. Question 41 asks the ratio of the wavelength of AM radio waves traveling in a vacuum to the wavelength of FM radio waves traveling in a vacuum is approximately blank. Okay, so we're looking at the ratio specifically between AM to FM in terms of their wavelengths. And so I have here towards the bottom the electromagnetic wave spectrum. So I'm going to expand this so we could find what we're looking for. The wavelength measurements are at the top. And here we have radio waves spanning this way. They have FM over here and AM over here. So we can see that AM has the longer wavelengths towards the right side, and FM is a little bit shifted to the left where it's shorter. So we're going to expect the bigger number to be on the AM side, on the left side. So AM falls somewhere between 10 to the second and 10 to the third. FM radio waves fall between 10 to 0 and 10 to the first. So let's just take the right edge of it. So I'm going to write here 10 to the third to 10 to the first. You can almost simplify it also if we take the left end of it as 10 to the second, 10 to the 0, which is the same as 10 to the second to 1. Anything to the 0 power is 1. And that's why choice 3 is our answer for number 41. So I'm going to get rid of this table. There you go. A charm quark has a charge of approximately blank. Charm quark, so we're going to use our reference table to find that, and I'll pause it for a moment. Okay, so this is our particles of the standard model. I'm going to expand this. And we're looking for charm quark right here. It has a charge that is approximately positive 2/3 of E. E stands for elementary charge. 1.6 times 10 to the negative 19 coulombs. And so we gotta take 2/3 of that. It's definitely gonna be somewhere less. So it can't be those two. 2/3 of it will come out to approximately choice 2, 1.07 times 10 to the negative 19 coulombs. 1/3 of it would have been choice 1. Number 43, the diagram below represents a 3 ohm resistor connected to a 12 volt battery. Meters X and Y are correctly connected in the circuit. What are the readings on the meters? Alright, so we have here a battery connected in series with just a lone resistor of 3 ohms. Since there are no other resistors to share this voltage, the meter Y, since it's also connected in parallel, is going to be measuring a voltmeter. So the meter Y is going to have a measurement in volts. Voltmeter because it's connected in parallel. And this here is an ammeter because it's in series. Alright. So all this voltage here travels through as energy, picked up by the Coulomb charge, by the electrons. Gets spent here, all 12 volts. Now, because this is an ammeter, we have to calculate for current, and the way we do it is V equals IR. 12 volts equals I times 3 ohms. I is equal to 4 amps. So this measures 4 amps. And our answer choice is 4. Number 44, a toy airplane flying in a horizontal circular path completes 10 complete circles in 30 seconds. If the radius of the plane's circular path is 4 meters, the average speed of the airplane is blank. So speed typically is distance over time, since it's going at a constant speed in a circle typically. Now, we have here a time of 30 seconds. The radius is 4 meters. And then it completes 10 circles. The thing about circles is that the circumference gets you D. And that's equal to 2 pi r. So that's where the radius comes into play. So the way I'm going to calculate for speed is 2 pi r divided by t. So 2 pi r, 2 pi 4 meters divided by 30 seconds should get you somewhere of 8 pi divided by 30. So 8 times 3.14 approximately, that's about 24-ish divided by 30. That's about 4 over 5. That's 0.84 meters per second. I just did approximations in my head. There you go. Alright, so question 45 asks us to find which pair of graphs represents the vertical motion of an object falling freely from rest. In this scenario, your initial velocity is 0, so we start at 0. And when it's falling freely, It undergoes an acceleration of 9.81 meters per second squared. So this object is accelerating. That means displacement increases exponentially with an acceleration. Whereas the velocity changes at a constant linear rate. And that's choice 2. So a way to interpret this, when it's accelerating at 9.81 meters per second squared, that means each second that passes, its speed increases by 9.81. So each second, you add 9.81 to its speed velocity increases at a constant rate. So it has to be linear. And then displacement here changes exponentially, because as you increase your speed, you're not moving at the same constant rate. You're moving at an exponential rate. Okay, so number 46 has an object being thrown straight upward. And it's going to come back down. But we're just looking on the way up. And at this top point, the peak, it comes to rest. And so, as it's going upwards, it's fighting against gravity, because gravity will always act downward. Gravity is going to pull you downward as you go up, so it's going to slow down. So we can gather that there's a relationship here that as height, as height increases, kinetic energy decreases. And there's only one choice that shows that indirect relationship, and that's choice 1. Number 47, we have a slinky spring, and X is a particle in a spring. We have a longitudinal wave passing through the spring toward the right. Longitudinal means the particles vibrate parallel to the direction of motion. So they vibrate parallel. If the spring is moving, or the wave is moving to the right, that means the particles are going to vibrate side to side, left and right, because it's parallel. And that's choice 2. If you were stuck between choice 2 and 4, this here is transverse, that's perpendicular. Those you see more often with sine curve-like waves. Number 48. We have two wave pulses, x and y, traveling towards each other. They both have amplitudes of 0.3 meters that are directed upwards as crests. Which diagram shows the pulse produced due to the superposition? This is another name for interference. Keeps forgetting to switch to pen. It's another name for interference. So what happens when these two waves superpose or interfere with each other? Now, because it's crest and crest together, this is going to be constructive, which means they add up. So then 0.3 plus 0.3 together will make an even bigger wave, bigger amplitude, and that's 0.6 meters high, choice 3. Horn of a car produces a sound wave of constant frequency. The car traveling at constant speed approaches, passes, and then moves away. It approaches, passes, and then moves away from the stationary observer. Which graph best represents the frequency of the sound wave detected by the observer during this time interval of approaching, passing, and moving away? So moving towards or approaching, leads to higher frequency. Away, as it moves away, the frequency decreases. This is the Doppler effect. Now as it passes, it kind of goes, it's pretty much exactly the same frequency, as close as possible. So we're going to see sort of an increase in frequency and a decrease in frequency. And the only one that shows that is choice 3. It's higher and then it goes lower. And number 50, a combination of two identical resistors connected in series have an equivalent resistance of 10 ohms. So in series, two identical resistors. That means R1 plus R2 are equal to each other and they both equal to 10 ohms. So that means each resistor is equal to 5 ohms. But that's not what the question is asking for. This is only the first step. What is the equivalent resistance when they're connected in parallel with these same two? So now we're looking in the parallel equivalent resistance. So 1 over R1 plus 1 over R2. So this is going to be 1 over 5 plus 1 over 5 equals 2 over 5. Flip it over. We get 5 over 2. And this is equal to 2.5 ohms, choice 1. Okay. And that's it for part B1. That's the end of also the multiple choice section. So the next couple of videos, or the next 2 videos, are going to go over the free response questions.